All right. Good morning, everyone. Welcome to the July edition of the Ice Giant Systems Seminar Series. Just a little bit of housekeeping at the beginning. If you are not signed up for the listserv, I would encourage you to do so. That's where we get all of the updates. I'll drop the link in the chat here. If you're interested in giving a presentation for this series, feel free to reach out to myself or Jody Burtis here on the call. We're always looking for new speakers, new topics. Today we have Dr. Matjia Cuk. Thank you so much for agreeing to present here today. Matjia Cuk received his PhD in astronomy from Cornell University and was then CITA National Fellow at the University of British Columbia and the Dolly Clay Fellow at Harvard University and the Smithsonian Astrophysical Observatory. Dr. Cuk has been a research scientist at the SETI Institute since 2011. His research focuses on the orbital and rotational dynamics of planetary satellites and small bodies. In particular, Dr. Cuk has worked on the dynamics of small binary asteroids, early dynamical evolution of the Earth-Moon system, and on a possible recent origin of the rings and inner moons of Saturn. Dr. Cuk received the 2014 Harold Urey Award of the DPS, and the asteroid 5639 Cuk is named after him. So thank you so much for joining us. He'll be presenting on the orbital stability and age of the inner moons of Uranus. Go ahead.
Oh, thank you, Mallory. Everybody can hear me, right? Yeah,
we can hear you.
Thanks. So thanks for being here. You might not be getting the best version of me at 8 a.m. in California, but I'll try to deliver. So this is work I've done with a bunch of people at SETI and also Mariam now at SWIRI. The paper has been out for 2 years. I'm going to talk a little bit more about that, but you can look up the paper in AJ on the stability on inner moons of Uranus. Okay, so with moons, like with everything else, the few celebrities get all the attention. And at Uranus, it's the 5 big moons that everybody knows about. So there are these 13 small moons interior to Miranda. They're often called ring moons, and 10 of them were discovered during the Voyager 2 flyby. And then 3 more were discovered since, either through Voyager 2 data or through HST. So I'm going to talk to about 2 groups of moons that are just bunched up in same major axis. So there is so-called Belinda group here circled in yellow, which is Belinda, which is a big moon, and then 2 small moons, Perdita and Cupid, that orbit very close to Belinda. Both Perdita and Cupid were discovered later after the flyby. And then the other group of very closely spaced moons is the Portia group, circled in blue, which has Cressida, Desdemona, Juliet, and Portia. Portia is the largest of them. Okay. So why do we care about stability of these things? If they're there, they must be stable. Well, starting with Duncan Lee Sauer in '97, people doing direct numerical simulations of the dynamics of these moons. So this is just put it in the integrator, run the integrator, see what happens on the gravity alone. They found that the Portia group, that's the inner group with the 4 closely spaced moons, is unstable on different time scales. Now depends what you assume for densities because we don't know their masses. Also, initial conditions were not always well known, but their stability is in the millions to 100 million years. And that's weird because solar system is 4 billion years old. And then more recently, as more moons were added to the system, they started becoming even more unstable. So the paper by Rob French and Mark Showalter in 2012, where they showed that the new moon Cupid, that is very close to Belinda, is actually unstable on 100,000 year timescale. Now that's super short. We really should not be seeing this thing. And they also confirm prior results that the Portia group is unstable. So we, the dynamicists are a bit like plumbers. You come in and you say, oh, who did this? Let me do it better. So we decided that maybe we can redo this. And one reason is that you might have better data now because the SETI Institute group led by Mark Showalter has been observing these moons and getting better positions and orbits. And also, we might assume some things about their densities or maybe tidal dissipation that might stabilize them. We were thinking tides might help here. Now, this point is a question, so you know the answer is no. And we used Hal Avison Swift RMVS 4 symplectic integrator for this. It's one of the standard integrators. This one has a special thing that every time you run it, it gives you the same thing, regardless of what low mass particles do. Okay, so the Belinda group, so that's Belinda, Perdita, and Cupid, turned out to be much more stable than originally thought. Rob French had 10 to the 5 lifetime for Cupid, but we managed to have them stable for tens of millions of years. And the reason for that is this really weird mean motion resonance between Belinda and Perdita. So if the two moons are close to the resonance, they interact with each other strongly and become unstable. But if they're in the resonance, exactly, that stabilizes the system. Now, this is 44 to 43 resonance. It's really, well, it's not high order because the order is the difference between these numbers. So it's the first order resonance. But the fact that these numbers are so large, that tells you that the orbits are very closely packed. And we don't see these things too often. So for here, we have resonant argument, if anybody cares about such things, but it just shows you that the resonance is real and it's pretty stable over tens of millions of years. And we managed to get this thing stable, the Belinda group, for about 50 million years. After that, Cupid starts wobbling and a system is not indefinitely stable. Now, the important thing is that we assume densities of 0.6 grams per cubic centimeter, which is about what you expect for bodies that are close to their Roche limit. If we double the densities, for example, for the same orbits, everything the same, the Belinda group becomes unstable. So this kind of puts constraints on what the densities of these moons should be. And we don't have this data otherwise, so that's great. The kind of the downside is that it's not really that surprising. We know that these things are close to their Roche limit, so no great news here. Now, then we move to Porsche group, which multiple groups of researchers have found to be unstable, and you can see that the core Porsche group are 4 moons packed really closely together, and then on the wings there are smaller moons like Bianca and Rosalind, which do not affect the big ones. If you look at the radius, these 4 moons in the middle are bigger, and then mass goes as radius cubed. So we'll ignore the side moons because if they're not stable, if the 4 of them are not stable just by themselves, they're not going to be any more stable with 6 moons. And well, we can get, depending on the assumptions of density and so on, we can get them to be stable for a few million years. But you can see what Cressida and Demona, for example, are doing. For a while, they can be well-behaved and they get chaotic. These moons are just not happy. And what I'm showing is just 6 million years. We can play with densities. Cressida has been, the density of Cressida has been determined by its interactions with one of the rings. It's just below 1. Exactly what you expect if Cressida is at its Roche limit, so no surprise there. Then we can play a little bit because there are errors on the albedos and sizes from Voyager, and if you assume that everything has same albedo, then you actually get slightly more stable system. But yeah, we get to about 50 million years again, and in between, you see, it's not like Belinda group, which is stable, and boring until it goes crazy. This is once again the Desdemona. Throughout these 50 million years, the orbit keeps changing. That nothing is constant, really. So these moons are just not happy intrinsically. And no amount of adding different assumptions or tides or anything could help. So I don't even remember what these 4 sets are now, what assumptions we used, but these are all sets of 10 systems that are very slightly different, and see how long they live. So some assumptions will get you like most of the systems living past 50 million years, but that's about it. And they're not stable eventually. And also I should add that integrating this is extremely time consuming, because the orbital periods of the moons are way below 1 day. And we are talking about tens of millions of years. So that's lots of orbits. So what really clinched it for us that Porsche group cannot be stable is new data that came out on Rob French's DPS poster. So this is one of those things that, you know, it is part of the literature, but it's really not, because it hasn't been really published. And the important part of the new data that came out with the poster is that Juliet, that's the second largest moon of the Porsche group, is eccentric. Now, you can see in this column is eccentricity, and Juliet's eccentricity is 10 to the minus 3. Now, if you can tell me that you can see that ellipse with the eccentricity of 10 to the minus 3 is different from a circle, you'll be lying. There's no way you can tell. But for these moons, because they're so closely packed, this is significant eccentricity. And it's even more significant because Cressida and Desdemona, which are less massive, exchange eccentricity with Juliet. So if Juliet has this reservoir of eccentricity, sooner or later we'll pass them to Desdemona and Cressida, which means that the system is already doomed. There is enough eccentricity in the system to go around for them to eventually collide in tens of millions of years. So we managed to stave off the death of Cupid, but not all moons are stable, and we keep running into this 50 million, 100 million year horizon. So then we started looking at tides. So these are tides within Uranus. So how do the orbits of the moons shift over time? And on the y-axis, we plotted the fraction of the orbit in terms of same major axis that the moons will migrate over 1 billion years. And on the x-axis is just distance. The horizontal dashed line is the synchronous orbit. Now, doesn't really matter what kind of tides you use. The equilibrium tides, normal modes, whatever. The moons will always move inward if they're interior to the synchronous orbit, and always move outward if they are exterior to synchronous orbit. So you can see, except for Puck here, which is just exterior to synchronous orbit, the other inner moons will be moving inwards. And the amount of tidal migration, relative tidal migration that Porsche gets, Porsche is the largest moon, so we are assuming that the tidal evolution is classical, so that's proportional to mass. Porsche is moving about 1% of its distance over a billion years, which is comparable to what we expect for Ariel or Miranda. And Porsche is moving inward towards Juliet and Desdemona and Cressida. And since Juliet and Porsche are separated by about 2% of same major axis, Porsche moving inwards by 1% is actually quite significant. So system might have been more stable in the past. And the tides are actually making the stability worse over time as the system is getting tighter. So other way to figure out which way the moons are moving is to look at the resonance. So we have one single resonance in the Uranian system, this one between Melinda and Perdita, the 44 to 43. And to make a resonance, you need a convergent migration. So if you don't know anything about dynamics, it's one good thing to know, that resonances are made if you migrate towards each other, and if you migrate away from each other, if two planets or moons are divergent, they will jump through the resonance, get a kick to their orbits, but will not get captured. So you need Belinda to move outward, or Perdita, the outer one, smaller one, to move inward. Usually bigger moons migrate more due to tides or ring torques. And in this case, ring torques seem to be a better explanation, because tides should move Belinda inward, and ring torques should move it outward. Now, the rings of Uranus are kind of pretty low density right now, so you wouldn't expect them to create ring torques on Belinda. But if there were more massive rings in the past, that would have affected Belinda, because Belinda has some of the major resonances interior to Roche limit, because the moons interact with rings through their mid-motion resonances. So Cassini division itself is caused by the 2-to-1 resonance between Mimas and the ring particles. So similarly, Belinda would have its 2-to-1 resonance where the ring would be if there was a thick ring close to Uranus. Think about like ring of Saturn. And why would have there been a thick ring? Well, there is this general theory about ring-moon cycle that has first been proposed at Mars by Hasselbrook and Minton, and then they expanded to Uranus. So this is kind of a busy diagram, but the important part is that there are different definitions of Roche limit. There is the rigid Roche limit, which is closer than the fluid Roche limit. Fluid Roche limit is how far you can have a ring. And a body with no strength will be a ring interior, like the material with no strength will be a ring interior to the fluid Roche limit and will become a moon if it moves beyond, that it can accrete into a moon. But then if a moon wanders inward, typically due to tides, to the inside of the fluid Roche limit, because it's rigid, it will not really be disrupted until you get to the rigid Roche limit, which is closer in, when you need stronger planetary tides. So there is a region where you can coexist, the rings and moons can coexist. And this also assumes that you are interior to the synchronous orbit. So you have two opposite kinds of tidal migration. So there's tidal migration outward. Sorry, I messed it up this time. Tidal migration is inwards, and the ring torques push you outward. As long as as the moon is interior to the Lindblad radius, which is basically means how close you need to be to the ring to have any major resonances in the ring and can interact with it. So if you're a very distant moon, you're too far from the ring to interact with it. But close in, you have major resonances in the ring. So while there is a ring, the moons will move out. And then once the tides take over and the ring is dissipated, the moons move inward. So you can have this cycle in which the moons are made, migrate out, come back in, are disrupted, make a new ring, and then make a new moon and so on. And every next generation will have less material. So in the past, before there was present Porsche group, maybe there was a more thick ring, more massive ring that created, Porsche group, and then the rest of it fell onto Uranus. And now Porsche group is migrating inwards, getting destroyed and remade until eventually it migrates into the inside the Roche limit and makes the next ring and so on. And the time scale for these things is hundreds of millions of years. So this is one possibility on what happens on long time scales and why we see unstable moons this late in the age of the system. Now, this is an interesting question. Is this what's happening at Neptune too? And the answer is no. The moons of Neptune seem to be very different in their dynamics from the moons of Uranus. So Marina Brozovic found that two moons of Neptune, the innermost two moons, Naiad and Thalassa, are in this really weird inclination type resonance. The interesting thing about this resonance is that if you put it together by tides, it takes billion years to put together. So these moons should have been around for a billion years. And that's very different from what we find at Uranus. Also, the moons of Neptune are not so closely packed, and nobody has found stability so far. They seem to be stable by gravity alone. And then this resonance between Naiad and Thalassa seems to indicate that their orbits have been converging slowly over a long time. So this is another indication that Uranus and Neptune might be different. And this is from a paper by Matt Hedman. He looked at the Roche limits for different moons, for moons of different planets. And generally, so the top section is Neptune, and this moon here is Naiad. So that's the innermost moon, the one that is in the resonance, and that should have been around for billions of years. It also defies Roche limit. Unless it's pretty dense, it has to have strength. So it's not a pile of rubble, as far as we can tell. while the moons of Uranus are a little bit further out and also coexist with rings, which are further out at Uranus than at Neptune. So the material at Neptune, the material of the inner moons of Neptune seems to be stronger, maybe more dense, but also maybe the moons themselves have internal strength. And more recently, we've been looking at how Naiad interacts with its own debris. Since it's inclined, it can get hit back by its own debris after a while. And that also indicates it has some strength. So moons of Neptune are not like moons of Uranus. Okay, so this the conclusions of this talk is that once we have the best, most recent orbits, we can show that the Belinda group, that's Belinda, Perdita, and Cupid, are actually stable on tens of millions of years. So they're not the most unstable part of the system. And the reason for their stability is that there is a resonance between Belinda and Perdita, which is the only known active resonance in a Uranian system right now. The Portia group, closer in, seems to be unstable. And that's pretty much the answer everybody keeps getting over and over. And the instabilities from 10 to 100 million years depends on the densities and a bunch of other things we don't know. So to put together the Belinda-Perdita resonance, there had to be a massive ring around Uranus relatively recently, whatever that means, maybe hundreds of millions of years. And there is a good reason to think that there is a active ring moon cycle at Uranus, that it includes at least Portia group, that these moons that are now unstable will keep colliding, maybe consolidating until they sink into the Roche limit, and then they might form a new ring from which the new moons would form. And because material is lost in every cycle, these cycles would have been faster in the past because tidal timescales and instability are faster for larger masses. And then very interesting thing, with at least that's how it comes across now, is that the ring moons of Uranus and Neptune are very different in their dynamical histories and physical properties. Don't know about the moral character, but they the moons of Uranus seem to be rubble piles that are put together, broken up, and put together again. And moons of Neptune seems to have been there for a long time and seem to be stable as far as we can tell. So I'll be very happy to take some questions. Thanks.
All right, thank you so much. Feel free to put your claps in the virtual reactions. Thank you so much. This was really interesting. If you have questions, feel free to raise your hand or put your question in the chat and I'll read it out loud. We have plenty of time for questions. And as you're thinking about your questions, I'll say that once we're done with the question and discussion period, Jody will put up some community news. We like to go through and look at potential job postings or upcoming meetings and whatnot, so that we feel like we're all engaged and knowing what's going on that's relevant to the ice giant community. So I don't see any questions yet in the chat. I'll ask a question. Oh, Mark, I see you have a question. I'll let you go first. Go ahead, Mark.
All right, thanks, Matjia. It was great, interesting talk. This is Mark Hofstetter from JPL. I just wondered if you had any speculations on why the Uranian and Neptunian moons are different.
Oh, that's a good one, and that's one I really wouldn't know. So the primordial difference between the two systems is that Neptunian system was messed up by Triton when it was captured. So we would expect actually the opposite, that the Neptunian system was the one that went through cataclysm, and Uranian system is what you expect of a system that forms together with a planet. Now, that's not how it is. And also, Uranian system is way weirder than we think because it has way too much angular momentum. Those moons are way too far from the planet. If you expect that the planet got its tilt from the collision, you really cannot preserve this large large regular moon system just like that. And there's been great paper by Raluca Rufo about that. So I would say I don't know, but possibly like one wild guess is that the capture of Triton might have reduced the amount of mass in the Neptunian system through the collisions and mass loss. So maybe that was a blessing in disguise, that they became more stable after they were decimated in the early cataclysm. That's just one guess. And then since they didn't go through through instability, their their material strength refers kind of reflects the fact that there are ancient bodies that formed maybe when they were slightly hotter and not just the rubble put together in the on the Roche limit.
All right, thank you.
So I have a question. Do the findings here have implications for how we understand the outer moons? Does it mean that the outer moons are younger than we would expect? Yeah.
Well,
yeah. What are the implications for the outer moons?
Yeah. So the original ring moon theory by Hasselborg and Minton for Uranus had this thing that maybe Miranda also migrated out from the ring. That would require some extra dynamics because Miranda cannot get where it is now through ring torques. So you need non-standard tides, which we certainly don't know are not there. There's lots of stuff we don't know about the Uranian system. So the ages of the outer moons are actually not a free parameter really because of some of the cratering constraints. And I would say they have to be ancient. But now I think for Miranda, is it like beyond 4 billion years? It's heavily cratered. So actually you don't know that it's not slightly younger than the others. But I think that there is not much scope from what we know that with a slight exception of Miranda, maybe early on and with some extra tides, there is not scope to form them much later than the beginning of the solar system for the main moon.
All right. We have a question in the chat from Michael Lucas. In some of your earlier plots in the talk, eccentricities seem to become unstable at about 3 million years. Can you elaborate on why you rejected these models?
Oh, they're not rejected really. We always we expect that if we see something, probably it's if it's there, probably it's somewhat stable. Like if it's stable for 30 million years, maybe we're more likely to see it than if it's stable for 2 million years. We don't really know until we know exact densities and sizes of these moons what stability timescale is good. And since we know in the end that they're not truly stable, it's really nothing is really rejected, and it's the internal instability that drives the collision. So meaning that the fact it happens at 3 million years is just because they decide, because of their own dynamics, the moons become unstable. Nothing outside affects them at any special time.
All right, we have a question from Matt Clement. Go ahead.
Hi, Matjia. It's Matt Clement. Really great talk as always. My question was about the 44 to 43 resonance. You said you need a really massive ring to make it. So I guess first part of the question is how massive, and then how long does it take to make for like reasonable densities? And then are there any other of the moons in the Belinda group that could go resonant before the system falls apart?
Yeah. So actually, we did this for a paper, and I had to remind myself, if you take Portia itself, or all the Portia group, Portia is most of it, and spread it around Uranus, you get a ring that has a higher surface density than that of Saturn. So just what we see there in terms of Portia group, if it was interior to the Roche limit, would be enough to form a sizable ring. And then that ring would have to be around for about 10 million years. That was our estimate to move Belinda enough. Now you can have more mass and move faster or something like that, but numbers are not unreasonable. Then we were also looking at how much, since Belinda's moving interior by tides, its resonances are moving with it. So at some point we'll come out of the resonance with Perdita, but also its resonances will catch up with Cupid. And we found that that takes about 50 million years until Cupid becomes unstable because its resonance with Belinda is catching up with it. That's separate from integrations I showed you because those integrations were gravity alone, no tides. But you can see the different timescales just give you upper limit to how stable the system can be.
All right, we have a question from Brian Palazewski. If the moon density is 0.6, does that imply that the moon is composed of only methane and water ices?
Oh, the general opinion is that these are, we don't quite know what they're made of. Water ice is probably a major part, but there's lots of void too. These are rubble piles. So the low densities usually reflect the fact that there's lots of empty space there, more so than that they might be made of very low density ices, which are not completely excluded. But like at Saturn, we know that the moons are made of water ice almost exclusively, the inner moons. And you got densities of 0.6 grams per cubic centimeter. And we think that that's just because of the voids.
All right. Oh, Jody has a question. Go ahead.
Yeah, really great talk. I'm just kind of curious, if you think that there are any, data or measurements that something like a Uranus orbiter and probe could take that you think might kind of further this research a little bit or in some way help out your models.
Yeah, so I'm kind of dynamicist who does things over like billions of years. So exactly what happens in a short time scale, you should ask JPL people or something. But I think that following these moons for a little bit would give you their masses, and that would really help you pin down the dynamics. At Saturn we have much better idea of all the masses, and then we also have things like Prometheus and Pandora, which is kind of a similar thing that they interact very strongly. So Porsche group is kind of like that. So yeah, I think just having an orbiter would get you masses because you have a constant monitoring of their motion.
All right. Of course, I'd love to see images of those moons, but we'll see. We'll see what we get. All right, we still have time for questions. If you have any straggler questions, feel free to put them in the chat. Keep thinking about them. For now, let's transition to Jody, who will put up the community news slide and talk a little bit about that.
Sure. Yeah, and like Mallory said, if you have a lingering question that kind of pops up, definitely just raise your hand, interrupt me. I'm cool with it. So as Mallory mentioned, we like to do this kind of community news slide. It's usually kind of quick at the end as we sort of scramble for the last, like couple minutes or something like that. But luckily I've got a good amount of time to talk, so I'm kind of stoked about that. But I'm always down to sort of have more conversation about the moon dynamics. So definitely interrupt me for sure. But what I'm going to do is actually, this is going to be really annoying and rough, but I'm going to put this in the chat. So beware of this incoming massive text. But sort of just so that you guys can have those links, because I know you can't really click on a PowerPoint slide that I'm sharing on my screen. So just real quick, the Ice Giant seminar, system seminar series next month in August. We've got Dr. Jessica Weber from JPL presenting. And so Mallory has I think both of us now have posted the link in the chat to kind of see the schedule of upcoming talks, and also to sign up for our listserv, which is sort of where all of our communication takes place. DPS abstracts and AGU abstracts are all coming up this month. So make sure you get your abstracts in. July 17th is DPS, July 31st is AGU. And then DPS also has, I think there are 2 different travel grant applications that both have their deadline of July 21st. So if you're hoping to get a travel grant, definitely apply to those. there are 2 professor positions at the University of Bern that are still open for about another month or so. One of them is in space instrumentation for experimental solar system exploration, and the other is planetary remote sensing and in situ mass spectrometry. So I thought those were kind of relevant for our group here. And then I added this one just this morning. I saw that there was a director of the LASP, the Laboratory for Atmospheric and Space Physics, that's at CU Boulder. So they've got a director position that's open, and it's open for the next month. And then, of course, the OPAG meeting was just announced. I believe it's virtual only, so that'll be in the first week or so of November. So save the date for that and check out that website for more info as the agenda and abstract solicitation comes online. And then I also saw this just this morning too. The DPS Professional Development Subcommittee is seeking members. So if you're interested in that, email Jennifer Hanley at her email address there to sort of express interest in joining that subcommittee. And I think that's everything I've got, so I can turn it back over to Mallory. Thanks, everyone.
All right, that's about it. I don't see any additional questions. Thank you so much, Matjia, for giving your presentation. It was really, really informative. And we'll give you all back a few extra minutes of your day. So take care, everyone.
Thanks, everybody.